I want to welcome all of you here to a new topic that will help you not only in your long essay or project work and dissertation, but it will also help you next semester under supervised machine learning. Oh, no, you guys are MBA, so it will rather help you in your long essay or in your project. You guys are doing research methods next semester, or you've done it already?
Not done it.
Okay, so it will also help you there. So the topic is known as logistic regression. As you know, we have already looked at simple regression and multiple regression. This is logistic regression. By the end of the study, you should be able to understand the theory behind logistic regression. You should distinguish between a linear regression from a logistic regression, and then build and compute logistic regression models. More importantly, you should be able to interpret a coefficient as well as evaluate the performance of a logistic regression model. You will do the analysis next time, in our last lecture, you do the practical application of logistic regression in Python, potentially on RapidMiner, okay, but more so on Python. So let's start with supervised and unsupervised machine learning. You are in the world of machine learning. I know you guys are not fully doing machine learning, but in the world of machine learning, we have something we call classification and regression. Regression is the one we have done. We've already looked at the linear regression, okay, where we assume that the relationship between the price and the quantity demanded is linear. When we say something is linear, it means that the relationship is downward sloping is linear, upward sloping is linear, vertical is linear, horizontal is linear. The only thing we are saying is that it's not a curve. 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 But the moment it is a curve, whether the curve is like this and goes like that, or it's like this and goes like that, or it's like this and goes like, whichever way it is, once it's like this, we are going in the world of logistic regression. Logistic regression. Because the relationship is no longer linear, but it's more or less non-linear. It's polynomial. It's quadratic. It's parabola. That is what is known as logistic idea. But then we'll get deeper into this. In a linear regression that we've looked at all this while, we know that the dependent variable is metric. What does that mean? It means the dependent variable is a number, a numeric number, a continuous variable. So you can look at the quantity demanded as a function of price, beta 1, and then you will have an error term usually. And the quantity demanded is a dependent variable, and this quantity demanded is a number. It could be a float, a continuous variable, a continuous number, or it can even be a discrete, but it is a number. It is a number. But in a logistic regression, the dependent variable is not continuous. It's a whole discrete integers, discrete number, or even it is nominal. Sometimes we say it is even binary or dichotomous. For example, the dependent variable alone will not be quantity demanded, but you can have a situation whether the thing is gender. So you have gender here, and gender is a function of something. I'm just using a linear to write it, but it's not linear. Okay, gender is a function of something, and that something is pregnancy. Okay, so gender is a function of pregnancy. So you know that inside the element of the gender or sex, we have how many levels? How many levels are there? And what are they? Let me see if I can get each person to speak today. Everyone. So Adokwache. How many levels?
Can you please come again with the question? I didn't really get.
How many levels are there when you have the dependent variable, like you see on the screen, to be gender? Gender has how many levels?
I said male and female binary.
Good. So it has 2 levels, male and then female. So what you are saying is that pregnancy affects. Oh, sorry, I think I made a mistake. Let me just correct that quickly. Okay. Let me just delete that. It's rather pregnancy is a function of, depends on gender. Okay. But then the one I'm looking for is not pregnancy. So in this case, this is a typical multiple regression or simple regression. But I'm more interested in looking at the probability of having cancer, okay, cancer or no cancer is a function of genetics. It's a function of genetics, or it's a function of something else. So the probability of having cancer or no cancer is a function of genetics. Okay. Or the probability of whether you will fail. Now, let me use that because you will understand that. Whether you will fail or you will pass research, statistics for business analytics. The probability of failing or passing is dependent on attending class, is dependent on doing your homework, is dependent on, okay, it's dependent on what other things? Who can tell me? It's dependent on which other factor? Yes, McAfee.
Doing your personal studies.
Okay, doing your personal study. What else? Adam.
Completing assignments.
Completing assignment. What else? Having study groups. What else? Paying attention in class and so forth. So you can see that several factors affect something, but that something is either failure or pass. Okay, so there are 2 possibilities. Okay, one is either failure 0 or pass 1. So you can see that the dependent variable, which depends on these independent factors, this target variable is what? Is binary. You can take a 0 or 1. And that is a classification problem. That is what a logistic regression handles. So here we are dealing with, we are dealing with labels like fail, pass, fail, pass, fail, pass. So when you have the column, I'll show you very soon. See that some of them will be fail, pass. Now, the same way I drew the simple regression line for you, this is how a logistic regression line looks like, what you see on the screen. It looks curvy. It looks curvy. It looks curvy. Okay. So I want you to look at a practical situation, some of the real life situation where you do. In fact, I was just going through with my students, 33 students who are doing their project work, and they were looking for topics, and some of them have chosen bogus topics. Well, by looking at these things, these are some of the topics you can do right now. Some of you are doing, all of you are choosing topics related to operations and supply chain, isn't it? Is that not what you've been doing?
No.
Okay. So your colleagues can some of you tell me the topics you are doing?
So we are MBA students.
MBA,
No,
we are
we
not
are
MSc.
MBA.
Yeah,
So
so
we
your
have
topics,
chosen our
some of your
topics.
topics are what?
You mean
No,
our
we are yet
courses?
to decide on those ones.
Okay. You've not selected your topics yet.
Yes.
Yes, please.
Well, believe you me, all the things I'm about to show you are powerful topics you can do. There's so much you can do on them. So the probability of, you can look at loan approval or loan default. Okay, in loan default, a bank will give loans to people. The probability that a person will pay back the loan or will not pay back the loan. The chances of paying or not paying depends on several things. And you can do this as a logistic situation. Credit allocation, whether we should give this person credit or not, buying or not buying a product, it is a binary situation. Default or no default, it's a binary situation, okay? Can have a situation where, and this is the one I'll be dealing with today, filtering the spam or not filtering spam, pass or fail. For example, somebody sends you an email. How is your emailing filter able to know that this is a spam? And then to move it to a spam. And this one is not a spam. It will move it not. It is because of a certain algorithm that has been put into the memory of the emailing system to be able to detect a spam. There are some keywords. So those keywords are in such a way that once the person uses those keywords in the email, no spam, you know very well that it's that things like buy, sell, and things like that. That is a binary situation and requires a logistic model. Medical diagnosis, whether a tumor is cancerous, it's not cancerous, whether that tumor is dangerous or malignant or benign or not harmful, that you can detect. The probability of that happening is a logistic situation. Some of you can do a research on fraud detection. Okay, whether a transaction is fraudulent or not. For example, if somebody who has not been taking money from the bank, all of a sudden he came to take 10,000. The next day he came to take 20,000. Then you know very well something might be wrong. You want to double check. What shows that this particular transaction that happens here is fraud. Fraud detection. This is an application of logistic situation. Web categorization. Which particular categories of web would you identify phishing? Okay. Whether the website is an adult website, malicious website, or actual website, you can tell using the logistic situation. And finally, customer churn prediction. Will the customers of EcoBank stop saving with EcoBank? What is the likelihood? Will they churn or they will not churn? What is the likelihood of canceling? What is the likelihood of attrition? Attrition. Okay. If it is not attrition, what is it? Either people are leaving or people are being retained. So attrition or retention. These are all binary, and logistic handles that. Which party is going to win the next election? The probability that NDC or MPP will win, okay? Would a person vote for MPP if they are the next election? Would they vote for it? It is a binary situation. It is a binary situation. There we go. And now for an online retailer, sometimes you want to predict which particular product a customer is most likely to buy. Okay. So you go and put things like Samsung phones and iPhone. Which ones are the customers most likely to buy? You receive a data set with past visitors. And from the past visitors, you are able to detect the likelihood of them buying what particular product. This is all applications of classification, logistic situation. Let's remind you a little bit about linear regression. Before we come to logistic regression, pay attention here. You have this in your exams as part of the compulsory, so pay attention and ask questions. Now, this is a linear regression model. Technically, the cap should not come because we will not finalize it. You can see there's a constant, and then, of course, you have the beta parameters. Beta 1 tells you the marginal effect of x1 on y. Beta 2 tells you the marginal effect of x2 on y. This is a multiple regression model. In an expanded form, this is the same multiple regression model. You want to put it all together, you want to create a matrix. This is the multiple regression model. So this is a linear regression that we know of all these well. Now, the target variable here is 1. Y is a single variable. It can be price, it can be quantity, it can be blood pressure, it can be wages, it can be salaries, it can be anything. So it is continuous. And these are some of the examples here. However, what if the dependent variable, the target variable, is not continuous, it's binary, it's a discrete binary? Let's look at the influence of age. Would you agree that a person's age can determine the presence or absence of disease? Would you agree with that?
Yes.
Good.
Yes.
What about gender?
Yes.
Yes.
Good.
Yes, certain
Would you
diseases.
agree that your smoking status can determine the presence or absence of your disease?
Yes. Yes.
So the dependent variable here is what?
Binary, 1 or 0.
And what is that?
Whether you'd have the disease or
Exactly.
not.
So the dependent variable is binary, whether you will get a disease or not. Now, in this case, it's no longer linear. It's not one item. It's either one or that. Okay. So, for example, you are going to say that the older you get, the likelihood of you getting the disease. So the older you get will lead to the presence of the disease. Let's say the disease is high blood pressure. The gender you are, I mean, whether you are male or female, which one is more likely to have the presence of a disease? Don't worry, there's no right or wrong answer. Which of them two gender is more likely to have a disease?
Any.
High blood pressure, adequate.
I think male.
Yeah, good. Smoking status. Whether you smoke or not, which one has got? Remember, these are binary. It's only age that is not binary. Okay, whether you smoke or not will have an effect on what? Presence or absence of disease. It depends on what kind of smoke. So let's assume that a person smokes. That leads to what? Absence of disease or presence of disease.
Presence of
disease.
Very good. So the key point here is that you can determine the probability of the occurrence of the categories of the variable. You can determine the probability of them leading to the disease or not to the disease. So this is a data set you have. We shall work on this data set next time we meet. The data set is made up of a person being diseased or not diseased. The first person is diseased. He is 43 years old. He is male and he's a smoker. The second person is not diseased. He's 18 years old. He is male. He's a smoker. The third person is diseased. He's 22 years old. He's a female and she is a non-smoker. The next person is diseased, 25 years old, male, non-smoker. Next person is not diseased, 45 years old, female, smoker. You can't predict. You can't predict. So based on this, what can we say the extent to which age and gender and smoking status actually, increases the probability of having or not having a disease? That is a crucial aspect of things. That is exactly how it works. One second. Okay. So far, so good. If you don't understand, you ask. So these are the continuation of the person. Now, the last person, is that person diseased or not diseased? The last person. Is the last person
Not
diseased? Not diseased.
Not disease.
Does a person smoke or not smoke?
It doesn't smoke.
Doesn't smoke. Is a person male or female?
Male.
Male.
Okay. So keep this data information in mind. So we can examine the effect of each of these features on the disease, say tumor. If there is an influence from any of these factors, from age, gender, or smoking status, if there is an influence, we can then predict how likely it is for the person to have the disease, given the age, the gender, and the smoking status. But my question to you is that why can we not use linear regression? And rather, we have to use logistic regression. Who can tell me? We've already mentioned it. Why can't we use linear regression, but rather got to use a logistic regression? Patrick?
Because we are dealing with a binary dependent variable.
Very good. Now, I decided to plot the data set. I coded them and plotted them all. And you can see on the axis here, you have something like the ages. I took just one of the variables. Then on the y-axis, you have disease or not disease. Disease being what? 0. So you can see that the disease is 0 here, and then the not disease is 1 there. Now, why do you think that most of the data points are at the top here and at the bottom here? Why do you think most of the data points are at the far top or the bottom, far bottom? Why? When I plotted the data. Why is that so? Yes, Adam.
Because it seems that most of the independent variables, like the gender, smoking status, and the disease, gender and smoking status, they are binary. So they are either 1 or 0. So they are up and down. They are not in the middle.
Exactly. That is not the exact reason why. No, in fact, like I told you, even on this axis here is age. I use the age, as you can see. That's what I used to plot the data. So what is on the x-axis here is age. What is on the y-axis here is the diseased or not diseased. Is the diseased or not diseased? So why, and my question is that why is it that majority of the data points are at the far top, all gathered on the horizontal top, and then all of them are gathered on the horizontal down? That's my question. Marilyn.
Okay, Doc, please, I want to give it a try. It's because the outcomes are just 2 options. You are either diseased or not diseased.
Which is a value of what?
0 or 1.
Exactly. It's because the outcomes here are 0 or 1. So it doesn't matter your age. So you can see that somebody's age was here, maybe it's 8 or something, 18. Another is here, another is here. It doesn't matter your age, you're going to be falling. The value of your disease level is either going to be 0 or 1. It's going to be one of them. It can't even be between them. It's not even going to be between, because once you get it between, it's like there's a 0.5 disease or something, but there's none. So you are either going to be matched. So if your age is, let's say that your age is 45 here. Okay. If your age is 45 and you are diseased, then you match the 1 here. So the 1 and the 45 will meet here. Okay. The 1 and the 45 will meet, and that creates what? A point at the 1. If you are not diseased, it creates a point at the 0. That is why all the scatter plots are showing the minimum value of 0 and the maximum value of 0. Okay, this is just a scatter plot. If you want to draw a regression line, what will you do? If you were to do a regression, you would throw a line through this, isn't it? So you throw a fitted line like this. Now watch carefully that fitted line is in such a way that you allow it to go up infinity, and it also goes down because it can cross down. It can cross down. That is it. So we are explaining some reason why this thing may not work. We are explaining the reason. So why not use the linear regression and be free? Why not use a linear regression and be free? Well, you said one reason you have said is that because the dependent variable is binary, but that is not only that. It's also because any linear regression you use will predict values outside 0 and 1. That's all we know. But linear regression assumes constant variance, which is homoscedasticity. But that is not going to work here. Because here, we are dealing with the probability of you being diseased or you not being diseased. Okay, so there are two reasons why, but you'll get a third reason later. Linear regression requires the values to be between 0, it can be negative, but it requires the values to be outside 0 and 1. But these values are restricted between 0 and 1. So we can't use linear regression. Also, linear regression assumes homoscedasticity, that the variances are constant. But here, when you check the variances, they are not constant. Okay. So why not use linear regression? No matter which value the independent variable will get, no matter what, whether your age is 5, your age is 10, your age is 100, you're still going to be diseased or not diseased. It's either one of them. So you are restricted between the 0 and 1. Okay. If we are to plot that, so because the values are going to be between negative infinity to a positive infinity, as you can see here, the lines below are not going to be working. It's okay. But the thing is that, in fact, I decided to plot a regression line on our data set. This is it. And you can see that y is a function of x minimally. The R square is 12%. If we are to stretch this line up and down, you see the ending part of the line is here. Let me show you. Because the last data plot is here. Oh, come on. This is the last data plot. And then this is the ending data plot here. So you have squeezed the values between age and disease like that. And what you are saying is that between these 2 points, okay, if we should stretch this, then negativities are going to happen for both age and disease. But age doesn't have negative values. Diseases don't have negative values. And that is what, if you have to stretch the line, it implies. So, if we use a linear regression, it could be a wahala. Okay. So, what does a logistic regression do now? It will estimate the probability of occurrence and not the value of the variable itself. In other words, unlike regression that will estimate the probability of you having quantity demanded to be this, if price is that. Okay, so we can normally do a prediction. In normal regression, we can do a prediction. For example, you can say that the quantity demanded is equal to 320 minus 14 price. So if I know the price to be 20, can I know the quantity? If I know the price to be 20, will I be able to know the quantity?
Yes.
What will be the quantity? If price is 20, what is the quantity?
What?
Good. So that will be the value. So you see, I didn't say that quantity will be either this or that. No. But in a logistic regression, you are predicting not the value, but the probability of the occurrence of the value. Occurrence or the non-occurrence of the value. That's why I said occurrence and not the value of the variable. So the equation will have to be transformed by restricting the value or the prediction of the rate to be between 0 and 1. Because we are just looking at U happening, which is 1, and U not happening, which is 0. In other words, you having a disease, which is 1, you not having a disease, which is 0. And to ensure that the values are restricted between 0 and 1, we have to use a logistic function. The logistic function is also known as a sigmoid function. A sigmoid function. Now, the sigmoid function looks like an S function. An S function. Okay. And this function is given by what you see down here. Every mathematical equation, it has a sigmoid function somewhere. And the sigma function is always f of z, which is equal to 1 over 1 plus the exponential value to raise to the power negative z. Where the z here is the item you are trying to predict. It is an input value in this sigmoid function. It's an input value in this logistic function. Now, if you want to take the exponent, it is going to be 1 over 1 plus the exponent of minus z. Not e raised to the power negative z, but then the exponent of minus z. Now, we are going to use this z for our regression, our y equation, our Q equation here. And so we're going to find that equation and bring it inside the z very soon. And then we will now manipulate the function in a certain way. I'll remind you something very soon. Okay. So look at how the function looks like. It looks like an S shape in our example here. Okay. If we apply the sigmoid to the sum of the weighted features, we will get a number between 0 and 1. In other words, we want a function, guys. We want a function that will help us to have the values of the disease or not disease to either be between 0 and 1. Regression will not give us that function because regression is negative to positive infinity. What we need is a function, and the only function in the world that can help us in this regard is a sigmoid function. Okay. And let's get some theories before we come and apply this sigmoid function to regression. Remember, I said a sigmoid function. I didn't say sigmoid regression. So we are going to take the sigmoid function later on, and then we will determine how a regression can borrow something from this sigmoid. And then once we understand that, we can now use it to run our logistic function or logistic model. But before that, let's get some theories. There is a theory on logistic regression generally, and the first item in the theory are called the odds. Odds, you got to know this terminology. What are odds? When we say the odd, okay, so when somebody say, what are the odds that Man United and Chelsea will win? What are the odds? The odds are 3-2. What does that mean? What does that mean? People use that language a lot. People use that language a lot. Can you use the language with the word odds and tell us the meaning of that? When we say the odds, what do you mean by the odds? Well, first of all,
Sir, please, is it a possible outcome?
Okay. So if I say that the odds of passing this exam are high, if you study well, what do I mean? The odds of passing the exam are high if you study well. What do I mean? Raise your hand and tell me.
So the probability or the chances
No.
are high.
Yeah, but what do I mean? Say that what I just said in a sentence. Don't just use one word for me.
Okay, so the chance of passing this exam is high.
Okay. Watch that word. That word chance, you also use the word probability. But let me take it in a simple language. What this means in this very example, the odds of passing the exams are high. If you study well, it means that there's a strong chance of passing the exam. That's what it means. So when people talk about odds, they're usually referring to the chance, the probability, the likelihood that something will happen. So what do you think is the opposite of the odds? Because the odds of passing the exams are high. So the odds here can mean what? The odds can mean being in conflict or being in disagreement. That's what it means. Because if you tell me that the chances or the odds of passing the exams are high if you study well, is that sort of, this being disagreement with yourself. Let's say, for example, we say the two friends are at odds over their decision. What does that mean? Two friends are at odds over their decision. What does that mean?
They are not in agreement.
Hey, Asha. Oh, sorry. You mean they are not in agreement? So it means that they are in disagreement, isn't it?
Yes, sir.
Exactly. They are at odds. So I want you to carry that idea of that sort of disagreement. Now, when we come to statistical probability, it's a little bit different because in probability here or in statistics, odds compare the chance. That's what you see I've written here. It compares the chance of an event happening to the chance of the event not happening. So the odds here compares the chance of an event, the chance that the event will happen, which is success, to the chance that the event will not happen, which is failure. So the odds of getting ahead are 1-to-1. What does that mean? The odds of getting ahead are 1-to-1. What does that mean? It means the chance of success is the same as the chance of the failure. That's what it means. The chance of success is the same as the chance of failure. So mathematically, how will you write the odds? What do you think? The odds are going to be the probability of the event happening divided by the probability of the event not happening. Will you agree with that? That's it. The probability of the event happening divided by the probability of the event not happening. Do you know that what I have here, I can define it as the probability of the event not happening, the denominator? Because the numerator is the probability of the event happening. And then the denominator here will be the probability of the event not happening. Because it is actually 1 minus the probability of the event happening, which is actually the probability of the event happening. Guys, are you with me?
Yes, dog.
Yes,
Yeah, we
God.
are here.
You said, who said we are here? Andrews. Andrew, explain what I mean. If you are here, explain. Andrew.
Hello,
And
Doc. Good evening.
go ahead. You go ahead. Don't even me. You go ahead.
You said the probability of event happening is the same as the probability of the event not happening. I mean, in other words, if we divide the event not happening against the event happening, we will get the same figure. That is 1.
So when you say against all odds, she succeeded, what does that mean? Against all odds, she succeeded. What does that mean?
I think in this case, it means that the probability was against her in the sense that her chances of succeeding was lower compared to her succeeding.
And yet,
She succeeded.
that's it. Okay, let's move on. So if the odds are equal to 1, it means that the two events have got equal chance of happening or equal chance of not happening. That's what it means. What do you think if the odds are less than 1? What does that mean? If the odds are less than 1. What would that mean if the odds are less than 1? We said if the odds are equal to 1, it means that the events are equally likely to happen. But if the odds are less than 1, Kwache,
So it means the odds that the event is unlikely to happen is more than the odds that the event will happen.
good. What
That's the
about greater
denominator.
than 1?
So that's when we have the odds that the event will happen, the success or the odds that the event will happen is greater than the odds that it won't happen. So the numerator is greater than the denominator.
Suppose the probability a patient has a disease is 80%. Okay, suppose the probability that a patient has a disease is 80%. What are the odds here? The probability that the patient has a disease is 0.8. What will be the odds? It will be point what divided by point what? Using the bar formula. Madeline.
No, please, 0.8 over 0.2.
Good. Which give you what?
Four.
4. Very good. So that is it. So if the so you see, once you know the probability, you should know the what? Once you know the probability of an event happening, you should be able to calculate the what? Say it.
The odds.
The odds.
Odds.
I don't want to get far before some of you now say that. So say I don't understand this. That's why I'm taking my time to break things down here. Okay. So this is a 4 that you have. So this 4 means that the patient is 4 times more likely to be diseased or not to be diseased. We just don't know which, but that is what it means. So if the probability is 0.5, what are the odds? If the probability is 0.5, what are the odds?
1.
1.
1.
And what does that mean? In terms of the
They have
event,
equal chance.
They have equal chance of happening.
or I don't want you to
Equal
stick to
chance
one.
of happening or not happening.
Now you're talking. They have the equal chance of happening and equal chance of not happening. If the probability is 0.8, what are the odds? If the probability is 0.8, what are the odds? You just did it.
That already, yes, it's 4.
It's 4.
4. What does that mean?
Event is more likely to happen.
Good. And if the probability is 0.2, what are the odds?
.25.
Which means the event is unlikely to happen. All right. Now, why are we connecting logistic regression with the odds and log of odds and logit? Pay attention here. We are talking about theories here. That's why you got to pay attention. Once you can understand this, remember from probability, we get the odds, but from the odds, we will get something. Now, the odds that we just found, you should know by now that they are ranged between 0 and infinity. I mean, these are some of the examples of the odds. They range between 0 and infinity. Because what? Who can tell me why they range between 0 and infinity? Who can tell me why they range between 0 and infinity? Come on, you got to be incredibly smart to tell me. Who can tell me why they range between 0 and infinity? Because probability is what? Yes, Marilyn.
It's between 0 and 1.
That's
so
it. So the odds must be between
0 and infinity.
Good. Keep that in mind. Now, because it's between 0 and infinity, logistic regression will not be able to work with it. Because logistic regression, the sigmoid function is between what and what? The sigmoid function is between what and what? It's between 0 and 1. Okay, it's between 0 and 1. So ideally, you shouldn't have used the odds. You should have used the probability, but you can't use the probability. So what the logistic regression will do is that it will take the logarithm of the odds. Taking the logarithm of the odds is called logistic transformation. Why is it doing that? It is doing that so that the values will be between negative infinity to positive infinity, which is like what all continuous variables are. All continuous variables are between negative infinity to positive infinity. So the logistic regression wants to look like a linear regression, and therefore it takes the log of the odds, the log odds, the log odds. This word log odds means logit, logit, logit. And this will make it look like a linear function. This is important. Now, what is a log odds? So first of all, you know the odds. Do you remember the odds? The odds are P divided by 1 minus P. Do you remember that? Okay, that's it. There's a probability of the event happening minus the probability of the event not happening. Now, I take the natural log of that function. That is the logit of the probability of the log of the odds. Okay, so in this case, P here is the odds. Now I take the log of this called the natural log of this. When you take the natural log of this, you get a simple, a linear function, a linear normal regression function. I'll later come and show you how I got this one. But when you take this one, you get this eventually. You see that very soon. And I've answered this already. Why do you convert the odds to the log of the odds or the log odds? And the reason is because of this. One, probability is between 0 and 1. And so you cannot model directly using a linear regression. Two, the odds are between 0 and infinity. So that is still not symmetric. Because for it to be symmetric, it should be between negative infinity and positive infinity. Because any symmetric function, like a bell-shaped function, is got 0 in the middle. It's got from negative infinity to a positive infinity. That is when we say the thing is symmetric. And we want the thing to be symmetric. And for that to happen, then we need to move away and convert the odds to the log odds. So log odds will bring everything between negative infinity to positive infinity, just like any continuous function might look like. This is perfect for regression, and this will transform the probability from 0, 1 to negative infinity to positive infinity. Oh, this is beautiful if you understand it. So beautiful. Now, if you have the probability to be 0.8, and we have to calculate the log of the odds, you're going to get this value. If you like, take a calculator, divide 0.8. Oh, I made a mistake. This is supposed to be 0.8 over 1 minus 0.8. Just a second, let me just address that quickly. 0.8 divided by 1 minus 0.8, which is actually 0.2. Remember? Oh, it's actually 0.2. My brain was just moving faster. Now we can correct that. So if you take the log, if you want to find the log of the 0.8 divided by 0.2, 0.8 divided by 0.2 will give you 4. The log of 4 will give you 1.386. So that is a log odds of the log 4. Now, what does that mean? A log odds of 1.387 corresponds to 80% probability. That's what it means. Because it's just a matter of, it actually corresponds to, the log of 4. Okay. And the 4 actually correspond to the 80% probability here. And this is interesting. Okay. This is interesting. So once you understand this principle of logs, you can understand logistic regression when we get there. So let's refresh our mind with everything we've done. First, the probability is always between 0 and 1. Is a chance of an event happening. The odds is the probability divided by the probability of the occurrence divided by the probability of non-occurrence, which is between 0 and infinity. Is a ratio of the success versus failure. The log odds is just between negative and positive infinity, and that linearizes the modeling process. Now, the logistic function, I told you, maps real values to probabilities. So if the value is real, it can map it to probabilities. And for that to happen, we can say that the sigmoid function or the logistic function is equal to 1 over 1 plus exponent of e raised to the power negative 2. Now, if z, watch it carefully, In a simple regression, just to remind you of something, in a simple regression, y is equal to beta naught plus beta 1 x plus error 10. Okay, that is a simple regression. I can just say that all the x's, there are many of them. So we have beta 1, beta 2, beta 3. Let's put all together so that we'll have just one beta like this. And then for the x, I'll have 1. Okay, this is a generalized case. Or in a simple regression case, it becomes this, where I've just ignored the errors. I can bring the errors or ignore the errors. That is the z. So this z function, okay, is representing the regression equation. The regression equation for what? For the linear. For the linear. For the linear. But now we don't want it in the linear form. We want it in what? In a sigmoid form. That is between 0 and 1. So we drop it into this function. Whatever we see z, we put in the linear function there. And let's do some manipulations. Let's do some manipulations. So we know that the dependent variable is binary. The y, which is a dependent variable, is binary, is either 0 or 1. Where 0 here is not diseased, 1 is diseased. So the probability that y is diseased, a patient is diseased, given all the other independent factors, is the probability. The logistic function assumes this that you see on the screen. It assumes this. So the probability that y is equal to 1 given x is the exponent of the linear function divided by 1 plus the exponent of the linear function. Now watch this. We can convert this to the odds ratio, which is that. This is the odds ratio. So this is the odds ratio, which is the probability of the occurrence of the event divided by the probability of the non-occurrence of the event. This will be equal to the exponent of the simple regression process. This time I've added an epsilon. Now, what the logistic regression will do is that it will use a logit link or the sigmoid function, okay, which is the input to the sigmoid, which is this. It will use that one. Okay, that is why we call it logit function or logistic function, because it's using the log. We are dealing with the natural log of the odds. We're dealing with the natural log of the odds, and that is why it is a log odds. So it is a log odds ratio. What is this? It is a probability of the event happening divided by the probability of the event not happening. Now, this two, P over 1 minus P is the odds. You take the log of that odd, boom, you get a linear function. You take the log of that odd, boom, you get a linear function. And how do you get that linear function? You get a linear function using something known as maximum likelihood estimation. Okay, you use the maximum likelihood estimation because the dependent variable is what? It's not linear. It is binary. So you can't use OLS, ordinary least squares, which we did when we were dealing with a simple regression. You're also using the maximum likelihood estimation, not because, another reason why you're using it is because the errors are not normally distributed. In the OLS, the errors are expected to be normally distributed. So that is why you use the OLS. But here, the errors are not normally distributed. Why? We know why. The reason why is because that function itself does not exhibit any linearity. And so we cannot have the residuals to be normal. And then finally, the probability itself is not linear. Okay. So all these three reasons are the reasons why we use the maximum likelihood estimation. So when I do the maximum likelihood estimation on these factors, okay, on the log of the odds, I'm going to get these values. The B caps. The caps here simply means they have been estimated. They are numerical values. And the error term is vanished because we are using maximum likelihood for non-normal, non-linear relationship to normalize things and to linearize things. Very good. So once you got this, once you've gotten these values, in fact, I didn't go through the mathematics. So from here to here, from this line to line, how to move from the maximum likelihood estimation all the way to get this beta cap is not a small boy. I have it as an appendix for those who want to look at it. Once you have gotten this value, you need to interpret them. So let's get them. So the first one is the beta 1. Look at the beta 1. The beta 1 is the one attached to the x. What does it mean? Well, the beta 1 is the change in the log odds for a 1 unit change in the independent variable. So suppose there is a change in the independent variable x1. Suppose there is any change. If it was normal regression, you know what we normally say? That if there's a change in this, you know what we normally say? We say that a 1 unit increase in the x1 would increase the y by the beta 1 unit. That's what we would have said. But here we are not saying that. Okay. Here, beta 1 is a change in the log odds, not the change in the y, the change in the log odds if the x1 increases by 1 unit. So if the x increases by 1 unit, how is that going to affect a change, or how is that going to change the log odds? Not change the y, but the log odds. And that is why sometimes the interpretation of the logistic regression can be a little bit tricky. But once you know it, you can interpret it nicely. And then you can also take the exponent of that, which is the odds ratio itself. We'll use the odds ratio later on when we start with a practical example. Look, when we go into the practical example, all of these things will be clear. But look at some beautiful analogy. If x is 0, what do you think will be the value of the log odd? If x, watch it here. If this x is 0, do you realize that we can find beta not cap? If x is equal to 0, then the whole of this side will be 0. So beta not cap will be the log of the odds. Okay. So you get a log odds ratio. That's what it becomes. You know how beautiful that is? It means that if x moves from 0 to 1, then the beta naught will be equal to what it was before, but it will rise by beta 1. Because watch it. If x is 1, then it means the only thing left here is what? If x is 1, then the only thing left inside the beta 1 cap x is what?
Beta 1.
You're left to the beta 1. That's what is left. So now that you have the beta 1, okay, you can easily find beta naught if you want. So now beta naught is not going to be equal to the log of the odds ratio. No, it's rather going to be what? It's going to be log of the odds ratio also rising by the beta 1 unit. These interpretations will be useful when we come to practical work. Okay, I'm going to end by summarizing how the maximum likelihood estimation works. I told you that it works by looking at there's an appendix to it. So let me just walk you some few things. Unlike the linear regression, which we have said many times today, which normally we use OLS regression or ordinary least squares, the logistic regression will use the maximum likelihood estimation, which means that if y is equal to 1, it means that the probability is equal to p. And if y is equal to 0, the probability is equal to 1 minus a p. We know this. Now, the probability of observing the actual y is given by this, of a particular y. Not all the y, one y. That's why we say Li is equal to p raised to the power y into, it's like, if you can remember binomial formula, that's how it's looking like. P raised to the power y, okay, and then 1 minus p raised to the power 1 minus y. That is for one outcome, one target, one dependent variable. Okay. Now, Then when you put all of them together for the entire data set, the likelihood or the probability of the whole data set, not for one of them, but for the whole data set, is going to be now a kind of a summation, okay, of all the LIs from 1 to n, okay. So it's just the same thing as the one before, but I'm summing them, sort of. This is known as the total likelihood, or the total probability. Now, we are going to maximize the log of this likelihood. This is a total likelihood. We are going to maximize this. We're going to push it further high, okay? Just as in regression, if you can remember, if you want the beta parameters, what do? You maximize, if you can remember that function. I just don't want to go there, but let me just remind you. If you have y is equal to y minus y cap, okay, and then we know that that's 1 minus beta naught minus beta 1 x, plus the error. Okay, minus the error. Okay, you apply the minus to all of them. So when you have this, what do? You now decide to, that's the E. In fact, that's the E. Then you square it. So you now square this. Then you sum it. So you now sum this. And then you expand it, and then you differentiate this whole thing, okay, with respect to beta 1. Okay, first you differentiate with respect to beta naught, second with respect to beta 1, and then you set it to equal to 0. If you can remember, we did this last 2 weeks. You set it to equal to 0 and find the beta 1. What are you finding? You are finding the beta. You are finding the beta. You are finding the beta. So that's the same thing here. So here too, you will maximize the log of the likelihood, the total probability. You maximize the log of that. And that will help you to find the beta. That will make the observed outcome, the binary outcome, most probable. That's why it's called probability, most probable. You maximize that. The maximization process is a very complex process, but let me just summarize it here. Okay. So first of all, you need to take the log, because we say log likelihood. So the likelihood was the one above here. This is it. Okay. Then what do you do with that likelihood? Remember, this is an entire summation of the likelihood. So you take the log of the probability plus 1 minus the y, okay, multiplied by the log of the probability. So what we did here is that this thing, we just took the natural log of everything. That's it. And how many parts are there? Okay. For those of you who have ever done this, for example, suppose you have quantity is equal to K alpha and then multiply by L beta. Okay. If this is raised to some power, so it's not linear. So if you want to linearize it, you take the natural log of everything. Okay, you take the natural log of whatever is on the left, you take the natural log of whatever is on the right. So you're going to have ln Q equals to, then you bring this one here. So you have alpha, okay, ln K raised to the power alpha minus 1. Then you come to the beta. So you do plus beta ln L raised to the power beta minus 1. So this linearizes the function. When you take the log, what you do is that you linearize the function. And that's exactly what I'm doing here. So I take the log of this, okay, which means that I have to take because this one multiply this to expand, and this one multiply this to expand, but each of them will have that as well. Okay, so you take the natural log of all of the function after kind of simplifying. So I take the natural log of this, which means that I will sum all of this, bring the y, take the natural log of the p, plus take this one, because the 1 minus that will come, then you take the natural log of the 1 minus p. Simple. So now you've been able to linearize it. When you look here, you didn't have linearization. It had a kind of a square, 1 minus y, and then you had y. So now you brought all of them down. Exponents have been linearized, logarized. Logarithm has been applied to it, and now you have a linear function. What do you do from here? First, you see this y here. And you see this P here, okay? We are going to substitute the logistic function inside this function, this log likelihood function. So this function, wherever we see the P, we are going to substitute it. Wherever we see the Y, we're going to substitute it. So this is the P. This is a probability. I told you earlier. Now here, I've decided to just make it X beta. I didn't want to bring the plus beta naught plus the error time. It will be so manya. So I decided to just take those that have the independent factors. So this is a probability. Remember, it was e raised to the power blah, 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 divided by 1 plus e raised to the power blah, blah, blah. So whatever I see pi in the above, I'm going to substitute the whole of this. That's what it means. Whatever I see pi here, okay, I'll substitute this whole thing there. And I'll substitute this whole thing there. That's what I'm going to do. Okay. Well, you don't need to fully understand. You can go through and check it. But when you substitute all of them, you're going to get something like this. You just check. I've just done a simple substitution here. Nothing has changed. No cry. There's no need to cry about a simple substitution. Once you've done this simple substitution, the rest is just take the first order derivative and then make beta the subject, basically. So here, you can take the entire first order derivative, okay? You differentiate we call it D ln L divided by D beta I. So you differentiate it with respect to beta I. And then you can get the value of beta I. Finito. So if the betas are 1,000, you're going to get the values of that. This is what maximum likelihood is doing for logistic regression behind the scenes. And the whole idea is to find the betas. That's it. Once you get the betas, your job is done. Because watch this. What are we looking for? We are looking for these betas. We already know the X because X comes from the data. So we are looking for these betas. Once you find the betas, you can take the natural log of you multiply the beta by the X, each X, then you take exponent of that, okay? You will get these two values, and then you divide this by that, and that will give you the probability. Once you get a probability, you use this function of P divided by 1 minus P to find the what? Odds. Once you find the odds, you can find the log odds, if you like. So let's say that you find the odds here, and the odds here is, say, 4. Then you now take the log of that odds, and it will give you 1.3 something. Now that gives you the value. So it is the log odds that you are looking for, but you need the beta to help you to get the probability. Then you need that probability to help you to get the odds. Then you need the odds to help you to get the log odds. Boy. This is masters, and this is what you are supposed to gather here. The software will do all of this for you, but you need to be able to understand what is behind the scenes. That is the essence of our presence in this room. So let's go back to our practical one that we had. We know that the probability of Y being diseased, okay, given all the independent factors, given all the other features, is this. This is a natural situation. But then if I take the exponent of this, I'll remove the exponent to become an index. In our example, the probability of having a certain disease, that's a P of a person being diseased, is given by all the elements. Remember that we had beta 1 age, beta 2 male or female. Okay, that's a gender one. And then beta 3 smoker. And then of course, your error. This part here is a linear function that we know. It's a function of, so the probability that a person is diseased is dependent on the age of the person, the gender of the person, and the smoking status of the person. That's what this function is saying. Okay. But then we can manipulate it slightly, okay, as you can see here. And these are the coefficients, beta 2, beta 3, beta 4, which we have to what? Find. And the only way we can find this is by first dropping, linearizing this function. That's basically what I mean. Linearizing this function. We need to determine the coefficient so that our model represents the given data. And to do that, Like to linearize a function, we use the maximum likelihood estimation to compute each of the B's or the betas. So when you are writing your own model, guys, when you're writing your own model for your longest, and many of you, I can tell you, more than 50% of you are likely to use this. When you write this, you have to particularize it to your own model. You see the way I've written mine? You got to particularize it to your own one so that becomes your model one in your longest or project or thesis. Okay, now let's assume that you've gotten the answers for the B's, the betas. How do you interpret it? Now, when you have finished the estimation, and when we come next time, you see that this was our own. When you finish the estimation, you will now realize that the log odds, this is the log odds. Remember, I told you that first we need to find the B. Once we find the B, we come and put it into the P formula to find the P, which is a probability. Once we find the probability, we now put it into the odds formula to find the odds. Once we get the odds, we need to now take the log of the odds for the log odds. So what you see here is a log odds. So the log odds is equal to negative 1.36 plus 0.03 age plus 0.40 gender male plus 0.63 smoker. The P that you see here is a probability that a person given age, gender, and smoking status values will be diseased. The probability that a person will be diseased, that is what this one is telling you. Now watch this. So that will be for next week. If we hold gender constant, smoking status constant, and we just want to interpret age, how do you interpret age? If you hold this one constant, the male, the smoking status, then what we are saying is that if you change age by 1 unit, if you change this age by 1 unit, the log odds ratio, you see, not disease will change. No, the log odds ratio is expected to rise by 0.03. But now, that is okay to interpret it like that. But the question is, somebody's going to say, what does that mean? I want it to mean like the regression one. You see, the regression one will normally say that a 1 unit increase in a person's age is going to increase his dying by maybe a certain percentage or something. That's how we normally say it. So what is this? The log odds ratio, the log odds ratio, the log odds ratio. Well, that is how you got to interpret it. If you want to know the exact thing, you got to change the multiplicative value. Okay. We'll look at that one deeply next time. But for now, note that we interpret the log, we check what the log odds ratio is going to be. Okay, for a diseased person whose age has changed. So the beta is talking about the change in the log odds when the independent variable increases by 1 unit. In other words, how a 1 unit change in the independent factor, in this case age, affects the log of the odds. And like I said, this is not so much intuitive. So normally we change the log of the odds using odds ratio. So rather use the odds ratio. You calculate the odds ratio. And you can calculate the odds ratio for each beta. Okay, because the odds ratio is simply equal to e raised to the power that beta value. So let's say you calculate the odds ratio and it's 1. It means there's no effect on the dependent factor. If it is greater than 1, it means that it increases the likelihood of that event, the probability of the event. Oops. And if it is less than 1, it decreases the likelihood of the event. So that event is disease. So it increases the likelihood of being diseased if the odds ratio is bigger than 1. You are increasing the chances of you having the disease. If the odds ratio is greater than 1, your chance of getting that disease increases. And if it is 1, your chances of getting that disease is the same as the chances of not getting that disease. And if it is less than 1, the chances of getting that disease falls. Okay, that is what it means. So let's take an example. Suppose you have beta to be 0.5. What do you think will be the odds ratio? Okay, it is 1.65. Who can tell me how do we get a 1.65 from 0.5? How did you get that? Do you know E, the value of E? What is the value of E? E is the natural log. And what's the value of the natural log? 2.718.
Yeah.
Okay, so you're talking about 2.718 raised to the power what? 0.5, which is the B. So you can check it. Somebody can check it and tell us that it's correct. So that is what gives you the 1.65. So once you know the beta value, you can easily find the odds ratio. Come on, you can find the odds ratio. I just showed you the formula for finding the odds ratio once you know the beta value. So you now get odds ratio to be 1.65. What does that mean? It means that a 1 unit increase in age, let's assume that this is for age coefficient. A 1 unit increase in age is going to increase the odds by 65%. Hoo-hoo. Hoo-hoo. Okay, so that is going to increase the odds. So the chances of you getting the disease or not getting the disease is going to be 65%. That's what it means. The effect of a 1 unit change in X in the predicted odds ratio, that's what it is. Now, let's take another one. Suppose we have this function and we are looking at the X1 here, which is 0.168. Okay, when you check the odds ratio for that, it's going to be 1.18, meaning that the odds will increase by 18%, just as this one increases by 65%. Remember, the percentage increment is after the point. And like I said, when we come to our own properly, you will fully get a picture. Now, there's two things you want to note before we end now. In a multiple regression, if you want to check whether a particular independent variable or a particular feature is statistically significant in influencing the target, you use the t-test. Use a t-test. And in fact, it's from the t-test we get the p-value. And if you can remember last week, we indicated that p-value is what you use to determine whether a particular independent factor is significant or insignificant. So we use a t-test, but the logistic regression is not giving you any t-test. What does it give you? Or we'll come and see next time in Python. It gives you the world test or the world statistic. Instead of the t-statistic, it gives you the world statistic. The world statistic is what it uses for the coefficient. Okay. And the null hypothesis is always the fact that the population, in the population means the beta parameters are insignificant. So they are being insignificant means that the beta parameters are equal to 0, which means they are useless. But then the world statistic will tell you they are not useless, they are useful. Okay. Just as the t-statistic, you want it to be bigger. And when the t-statistic is bigger than the critical t, you reject the null hypothesis. Here to the same thing, you reject the null hypothesis. Then when you go to the multiple regression once again, we normally check for the joint test. What is that? The joint test is where you test whether all the independent factors put together are significant. We did it last time, joint significance. Whether combined, these features have an explanatory power, significant explanatory power on the target variable. That's for the multiple regression. But we are not doing multiple regression. This is logistic regression. So in logistic regression, they don't use the F test. We rather use the likelihood ratio chi-square test. So this goodness of fit test is measured by the log likelihood chi-square ratio. You will see the value right there when we go to the practice. And a smaller one is better. A smaller one is better. Remember, in the normal regression, a bigger F test is better. A bigger T test is better. But in the log likelihood, the smaller is better. Very good. So those are the two main things that we use to determine the significance of the features individually and collectively. Individually using the word statistic, collectively using the log likelihood ratio, chi-square ratio. That's it. This is how you handle that. But then there is something else we'll do next time. And that is checking whether the model you have used is a good model. We will look at something called evaluation matrix, determining the performance of your values, whether your model is good. Normally, we'll use R-square in a multiple regression, but in a logistic regression, we don't use that. We use 5 different approaches, and it all starts with something known as a confusion matrix. Confusion matrix. Okay, so next time we're going to understand the confusion matrix, the true positive, true negative, false positive, false negative. You're going to understand that, from which you can now get the recall, you can get the precision, you can get the sensitivity, and several other things. Ladies and gentlemen, this is a theory of doing a logistic regression. So when logistic regression is put side by side with a multiple regression, how will you address that? Okay. Next week, when we finish that, I will also talk about the exams structure. Ladies and gentlemen, that brings us to the end. The entire caboodle.